Hi, I'm Arshia, and this is my Lab 3 presentation for Physics 1. In this lab, I used GlowScript to visualize the orbit of a star around a black hole and then calculate the mass of the black hole, and also to simulate the orbit or path of a spaceship around both the planet and its moon. So there were two parts to this lab. In the first part, I calculated the force parallel, and force perpendicular from the given orbit and used force net to calculate the mass of the black hole. In the second part, I calculated the force of gravity on all three objects, so this was planet, moon, and spaceship, and then found a speed for the spaceship that would ensure the desired result in the orbit to look like what I wanted it to look like. The fundamental principles, first of all, in this lab were universal gravitation and Newton's second law. So universal gravitation, we know this formula, it's given here. And then Newton's second law says that force net is equal to the change in momentum. And we can use that to say that the parallel and perpendicular components of the net force are equal to the parallel and perpendicular components of the change in momentum, respectively, which then gives us these two formulas. So in this first simulation, we were given the location of a black hole, which was just the origin, the mass of the star, and velocities and positions of the star at many different time points. And then we wanted to find the mass of the black hole. So we did this by setting force net equal to force gravity, and they also calculated the parallel and perpendicular components of the net force at each point in time. You can see this here because as it's doing its orbit, this orange arrow is force net, but then the blue arrow is force perpendicular, and the magenta arrow is force parallel. You can kind of see how the perpendicular and parallel components make up force net, and they differ during the orbit. So at each point, we just said force net is equal to change in momentum over change in time, and then parallel and perpendicular components of force net are equal to the parallel and perpendicular components of change in momentum, respectively. And then we set force net equal to force gravity because the only force in question is gravity. There's no other forces at play here if we consider the system to be the star and the surroundings to be the black hole. And so here you can see that the mass of black hole is calculated, this is big M in the universal gravitation formula, and then you've got force net equal, and then you've got star positions magnitude, which is just R, so you've got R times R, R squared, you've got big G, and you've got small m, or the mass of the star. And then I found the mass of the black hole at each point in time, and then averaged it out at the end to get a final mass. In the next simulation, we had the moon, the planet, and the spaceship, and we were given all the masses, and then wanted to find orbits for the moon and the spaceship, and speed values for the spaceship that would give the correct orbit. And the correct orbit in this case was an orbit where it wouldn't crash into the planet or the moon, but it would clearly be affected by the gravities of both. Like its orbit would clearly be affected by both the moon and the planet. And this was found just by guess and check experimentation after calculating the gravity forces and velocity and position updating both the moon and the ship. The system, it could technically be all three, but if we're focusing on the spaceship, the system is the spaceship and the surroundings are the moon or planet. But technically all three are in the system and the surroundings are everything else, because here you can see that I calculated the force net on the ship and on the moon and on the planet, and this was done, as you can see here, the force net on the ship is equal to the force of the planet on the ship and the force of the moon on the ship, and this was calculated using the universal gravity. And this was just done the same way for the planet and the moon as well. And then use this net forces to position update and velocity update both the moon and the ship. The initial velocity of the moon was given, but the ship's one, I just experimented and landed on these values, -0.5 and -127, and this gave me the type of orbit I wanted. Overall, there were some errors. Obviously, the speed values were just guess and check for the spaceship. Both simulations were just an oversimplification of, we didn't really consider any other forces at play. But overall, this lab was really helpful in learning about orbits, momentum, and how we can use momentum to calculate components of forces. It was asked what the difference was between force net and change in momentum. Technically, they're the same value. The difference is the representation. When we think about calculating it, even though we get the same value when we think about calculating it, for force net, you think add up all the forces, versus for changing momentum, you think about calculating the final initial momentum using velocity and mass, and then just subtracting. So it's what it represents that's different. Also, in the second simulation, if we added a black hole, everything would still contribute to each other. It would still add to forces. Like, again, you would just, calculate the force of the gravity of the black hole on everything else, and you would do the vice versa. But whichever one contributes more just depends on the mass and initial position. So again, a black hole would obviously usually probably have a huge mass, but it's possible that it wouldn't contribute as much if it was put really, really far away from the other three things. So it depends on both position and mass. Thank you.